An automated teller machine is essentially a duality of engineering, serving simultaneously as an impenetrable physical fortress and a highly delicate, high-speed robotic system. The manufacturing of this complex device begins with its foundation, the heavily armored vault, known in the industry as the safe or the chest, which is designed to protect the currency inside. Massive sheets of high-tensile steel, often up to an inch thick, arrive at the factory floor to be processed. Traditional mechanical saws are far too slow and imprecise for this task. Instead, a computer-controlled laser cutting machine, guided by precise digital blueprints, directs a high-powered fiber laser across the steel. The laser focuses intense optical energy to melt the metal locally, while a jet of assist gas, such as nitrogen, instantly blows the molten material away. This leaves a perfectly clean, slag-free edge. For the absolute thickest components of the vault door, a plasma cutter is employed. This machine creates a high-voltage electrical arc that ionizes compressed gas into plasma, reaching temperatures hot enough to slice through heavy steel plating with incredible speed. Once the flat panels are cut, they move to a hydraulic press brake. This massive industrial machine exerts hundreds of tons of force to bend the thick steel into the precise structural geometry of the safe. Bending the steel into a box shape, rather than welding multiple flat pieces together at the corners, significantly increases the structural integrity of the vault because it eliminates vulnerable seams. However, where the bent panels ultimately meet, seams are unavoidable. Robotic arms perform continuous gas-metal arc welding along these joints, ensuring deep penetration of the weld pool without overheating and warping the surrounding steel. To protect against sophisticated physical attacks using drills and cutting torches, high-security safes utilize a specialized composite armor. The welded steel shell acts merely as a mold. Inside the walls of this shell, workers arrange a matrix of hardened steel rods and dense ceramic nuggets. A proprietary high-strength concrete mixture is then poured into this cavity. When the concrete cures, it forms a composite barrier that defeats various tools. If a thief attempts to use an oxyacetylene blowtorch, the ceramic plates disperse the extreme heat. If they attempt to use a heavy-duty drill, the bit will either hit the freely spinning steel rods and bind up, or shatter against the incredibly hard ceramic pieces. The vault door is then installed, featuring a complex network of solid steel deadbolts that slide deep into the vault frame, secured by an electronic locking mechanism that resists tampering. Above this heavy fortress sits the upper cabinet, commonly called the fascia, which houses the user interface and computing hardware. Because this section does not hold cash, it does not require vault-level armor. But it must still withstand harsh outdoor weather, extreme temperatures, and daily vandalism. It is fabricated from thinner-gauge steel and lightweight aluminum. After cutting and bending, these parts undergo a rigorous powder coating process to protect them from corrosion. The panels travel on an overhead conveyor through a multi-stage wash system. High-pressure nozzles spray alkaline cleaners and iron phosphate treatments to strip away manufacturing oils, dirt, and microscopic oxides, chemically etching the surface to promote paint adhesion. The clean, dry parts then enter a climate-controlled spray booth, where automated guns apply a dry thermoset powder. The guns impart a strong positive electrostatic charge to the microscopic powder particles, while the metal parts are electrically grounded. This electrical attraction causes the powder to literally wrap around the metal, adhering perfectly to every corner, edge, and crevice without dripping or sagging. The conveyor then carries the coated parts into a massive curing oven baked at over 400 degrees Fahrenheit. Under this intense heat, the powder melts, flows together, and undergoes a chemical cross-linking process, curing into a highly durable, scratch-resistant, and weatherproof skin that is much tougher than traditional liquid paint. Next comes the meticulous assembly of the interactive components on the plastic and metal fascia. The main display screen is typically a high-brightness industrial liquid crystal display, designed to remain entirely readable even in glaring direct sunlight. It is bonded directly to a capacitive touch overlay. Unlike the thin glass on consumer tablets, this touch glass is incredibly thick and chemically strengthened through an ion exchange process to resist heavy impacts and hammer strikes. A privacy filter is permanently laminated to the glass, utilizing microscopic vertical blinds to narrow the viewing angle so that bystanders standing off to the side only see a black screen. Below the display sits the encrypting pin pad, or EPP. Manufacturing this component is an exercise in extreme security engineering. The keys themselves are stamped from stainless steel or molded from durable polymer, seated over a tactile membrane switch. However, the sensitive electronic circuit board underneath is entirely encased in a solid block of opaque epoxy resin, a process known as potting. Embedded within this cured resin is a tamper-responsive mesh, an intricate three-dimensional web of microscopic conductive traces. If a criminal attempts to drill, cut, freeze, or dissolve the resin with chemicals to tap into the keystrokes, they will inevitably sever one of these delicate traces. The moment the internal microcontroller detects an open circuit or an abnormal change in electrical resistance within the mesh, it triggers a catastrophic zeroization protocol. The chip instantly erases all cryptographic keys stored in its volatile memory in a fraction of a second, rendering the pin pad completely permanently useless and ensuring the user's data remains safe. The card reader is another highly sophisticated module installed in the fascia. Most modern machines utilize motorized card readers. The manufacturing of this component involves assembling precise miniature stepper motors, durable rubber drive belts, and sensitive magnetic reed heads. The physical entry bezel is often molded from translucent polycarbonate and includes internal radar sensors or electromagnetic field detectors. These sensors are calibrated to detect the anomalous shape or metallic signature of an illegal card skimmer attached over the slot, allowing the machine to instantly shut down and alert the bank if tampering is detected. The true mechanical heart of the machine is the currency dispenser, housed safely inside the reinforced steel vault. Its singular job is to precisely separate and transport individual banknotes from a compressed stack, a task far more difficult than it sounds because paper currency rapidly degrades, absorbs ambient moisture, gets sticky, or becomes badly crumpled in circulation. The currency is loaded into heavy-duty polycarbonate cassettes. These cassettes are injection molded under high pressure to ensure strict dimensional stability. Inside each cassette, a spring-loaded mechanical pressure plate pushes the stack of bills continuously toward a front door. When the cassette is inserted and locked into the dispenser module, a mechanical lever automatically slides the cassette door open, exposing the very first bill to the dispenser's picking mechanism. The picking mechanism relies on a meticulously engineered friction feed system. Specialized pick rollers made from a specific durometer or hardness of polyurethane rubber rest directly against the first banknote. The exact chemistry and texture of this rubber are crucial. It must maintain precisely the right coefficient of friction. If the rubber is too smooth, it slips fruitlessly on crisp new polymer bills. If it is too tacky, it creates too much grip and pulls multiple bills at once. A high-torque stepper motor drives the pick roller, rotating it just enough to slide the top bill downward into the transport path. Right below the pick roller sits a counter-rotating retard roller, which spins in the exact opposite direction. The physical gap between these two rubber rollers is meticulously calibrated to be exactly the thickness of a single standard banknote. If two bills happen to stick together and enter the gap simultaneously, the counter-rotating retard roller catches the bottom bill and forcefully pushes it back into the cassette, allowing only the single top bill to pass through the pinch point. Once separated, the single banknote enters the transport path, a high-speed highway consisting of continuous polyurethane timing belts and freely spinning idle pulleys. The belts firmly grip the outer edges of the note, propelling it upward and out of the vault toward the presentation slot. Along this transport path, the bill flies through a gauntlet of advanced sensors at speeds exceeding 1 meter per second. First, a series of infrared optical sensors track the leading and trailing edges of the fast-moving bill. The main computer monitors the exact microsecond the beam is broken and restored, calculating the bill's speed and position to ensure it hasn't skewed or jammed. Next, the bill passes through the most critical sensor in the entire machine, the thickness sensor. This is typically a linear variable differential transformer, a highly sensitive electromechanical transducer. As the bill passes under a finely tuned tracking wheel, the transducer measures the physical vertical displacement of the wheel down to the micrometer. A single standard banknote might be exactly 0.1 millimeters thick. If the sensor reads 0.2 millimeters, the logic board immediately knows that two bills have managed to stick together past the retard roller. If a folded bill, a taped bill, or a double bill is detected, the dispenser's brain triggers an electromagnetic solenoid in a fraction of a second. This solenoid instantly flips a mechanical diverter gate located further down the high-speed transport path. The curved diverter forcefully redirects the flawed or stuck notes away from the customer presentation slot and drops them down into a separate, secure reject bin, commonly known as the purge bin, ensuring the customer never receives incorrect change. If the thickness sensor confirms the bills are perfect, they continue up the path to the stacking wheel. This is a rapidly spinning plastic drum fitted with curved, flexible tines spaced closely together. As the bills shoot horizontally out of the transport belts, they slide perfectly into the empty gaps between the spinning tines. As the wheel rotates, it gently strips the moving bills from their forward momentum and stacks them neatly onto a flat presentation carriage. Once the exact requested number of bills has been cleanly stacked, a mechanized clamp drops down to secure the entire bundle. A secondary series of heavy belts then drives this clamped bundle forward through an automated security shutter door in the upper cabinet, presenting the cash to the customer. If the customer is distracted and fails to take the cash out of the slot within a programmed time limit, typically 30 seconds, the transport belts automatically reverse direction. The mechanized clamp pulls the bundle back inside the fascia. The shutter door closes, and the bundle is dropped straight down an internal chute into a dedicated compartment within the purge bin, ensuring the money is not left exposed to the street. Bringing all these complex systems together on the final assembly line requires precision and strict environmental controls. Workers use pneumatic hoists to gently lower the upper cabinet onto the top of the heavy vault, bolting them securely together from the inside so that absolutely no fasteners are exposed to the outside world. Thick, copper wiring harnesses are carefully routed through specific internal channels. These communication wires are heavily shielded and physically separated from high-voltage alternating current power lines to prevent electromagnetic interference from corrupting the sensitive digital data signals. The core computer, which is essentially a ruggedized industrial PC running a specialized, highly secure embedded operating system, is installed securely in the upper cabinet. It connects to the dispenser, the card reader, the receipt printer, and the EPP using secure serial or USB connections. Every single communication line inside the machine is encrypted at the hardware level to prevent internal wiretapping or man-in-the-middle attacks by a technician. A heavy-duty power supply unit featuring a built-in uninterruptible power supply, or UPS, is wired into the base. This massive battery ensures that if the local electrical grid fails catastrophically right in the middle of a transaction, the machine has enough stored energy to safely complete the physical dispense, return the user's card, record the transaction in its permanent database, and shut down gracefully without corrupting its hard drive or leaving cash jammed halfway in the belts. Before any unit is allowed to leave the factory, it undergoes exhaustive and brutal quality control testing. In the environmental testing chambers, random production units are baked at extreme desert temperatures, frozen to sub-zero climates, and subjected to 99% humidity. while robotic fingers continuously punch the keypad and insert test cards over and over. This simulates years of extreme outdoor weather in just a few weeks. On the massive vibration table, the machines are violently shaken in 3 dimensions to replicate the extreme kinetic stresses of global freight shipping, and to prove that no internal cables or socketed chips will shake loose. The most intensive phase is the physical dispense testing. Technicians load the cassettes with thousands of specially designed test notes made of synthetic paper that perfectly mimics the exact weight, porosity, and friction of real currency in various states of decay. The machine is commanded by a diagnostic computer to dispense hundreds of thousands of notes continuously, day and night. Engineers closely monitor the reject rates and jam rates, analyzing the telemetry to ensure the diverter gates are firing with absolute millisecond precision. The receipt printer is also aggressively tested. This module utilizes a thermal printhead containing a dense row of microscopic heating elements. A tiny stepper motor pulls heat-sensitive paper over the head, and the microscopic elements rapidly heat up and cool down, literally burning the text into the chemical coating of the paper without ever needing liquid ink. A motorized rotary blade must cleanly shear the paper for hundreds of thousands of cycles without dulling or binding. Finally, security features are verified by intentionally simulating physical attacks on the cabinet, deliberately triggering the internal seismic sensors and thermal sensors designed to instantly detect the specific high-frequency vibrations of a reciprocating saw or the rapid temperature spike of a cutting torch. When a user walks up to the finished, fully commissioned machine in the real world, a breathtaking symphony of digital cryptography and mechanical action unfolds in seconds. The user inserts their debit card into the slot of the motorized reader. As the card breaches the bezel, a mechanical shutter drops open, and rubber drive rollers instantly pull the plastic card completely inside, securing it out of the user's hands. The reader precisely aligns the card and lowers a block of microscopic gold-plated contact pins directly onto the tiny metallic pads of the EMV chip embedded in the card. The machine's power supply provides a tiny electrical current to the chip, waking up the microscopic computer processor hidden inside the plastic. A highly complex cryptographic handshake occurs instantly. The machine digitally proves its identity to the card, and the card proves its undeniable authenticity to the machine, generating a unique, one-time cryptographic transaction code that can never be reused. The screen then prompts the user for their PIN. As the user physically types on the stainless steel keypad, the encrypting PIN pad acts immediately. It encrypts the keystrokes at the exact hardware level using advanced encryption standard algorithms. The raw, plain-text PIN never actually enters the main computer memory. It is instantly mathematically transformed into a completely unreadable cipher block. The computer packages this cipher block, the requested transaction amount, and the chip's unique one-time code into a secure digital payload. This encrypted message is routed through an Ethernet network cable or a cellular LTE modem connection to the bank's centralized host server. The distant host server receives the payload, decrypts the PIN using its own highly secure hardware modules, verifies the account balance in a fraction of a second, and sends a digital authorization message back down the line to the machine. Upon receiving this authorization, the main computer sends a heavily encrypted physical command down the internal cables into the locked vault to begin the mechanical dispense sequence. The dispenser's internal logic board decrypts the command, verifies its authenticity, and engages the powerful stepper motors. The polyurethane pick rollers spin to life, friction feeding the bills from the cassettes one by one. The retard rollers actively prevent doubles, while the thickness sensors verify the structural integrity of each fast-moving note. The diverter gates stand ready to instantly route any questionable bills to the purge bin. The pristine bills are rapidly stacked in the presenter drum. The external security shutter door rolls open, and the heavy belts push the perfectly counted cash out to the waiting customer. Finally, the thermal receipt printer rapidly burns the transaction details onto a slip of paper. The rotary auto cutter slices it cleanly, and the motorized card reader reverses its belts to gently eject the debit card. Deep inside the steel vault, the mechanical clamp returns smoothly to its resting position. The secure logic board completely locks down its digital communication lines, and the intricate machine goes completely silent, waiting in quiet, heavily armored precision for the next transaction.